Thanks for having me here for the talk. I'm going to tell you about some work that we're excited about over here. We did it quite recently. We've been working on methods for implementing semi-definite programs on quantum computers for some time. This has been work, especially with Dhrumil Patel, who I think Siddharth might know, and I think people actually at IIIT Hyderabad know well. So with Dhrumil, we've had a number of papers, and then recently Michele joined Cornell in fall of 2024, and Nana Liu has been a regular visitor to our group for the past few years, and so she visited this past April, and we completed this work recently. And what I like about it is that we can give guarantees of the runtime of the algorithm. It's a variational quantum algorithm. It's often the case that with such algorithms, they encounter many difficulties. But with this one, there's a certain sense in which we can give strong convergence guarantees. And so I'm very pleased with this work. Okay, and then as the talk progresses, we'll talk more about possible difficulties in realizing this algorithm in practice. Okay, so let's start with some introductory comments. Quantum mechanics and semi-definite optimization go hand in hand. This is something I did not realize when I first started learning quantum information. When I was a graduate student, I did my master's at Tulane and completed that in 2004. And at the end of my master's, I learned about the possibility of quantum computing and how it was very interesting. And so it really took my attention, like it has with so many people now. And as I was learning quantum information in my PhD, I didn't really work with semi-definite programs so much, but I saw that other people were using it for various purposes. And I guess it was something that I tried to avoid learning, but it's kind of inevitable due to this intertwining of these topics, that if you're going to be doing quantum information, you had better learn this tool. And so it's kind of unavoidable. And then as I learned it, I learned more and more about it and became more interested in the underpinnings of it. Like, how does a semi-definite programming algorithm work, right? And so now I've learned a number of techniques, and I was very happy with this work to be able to produce an algorithm that I understand and that I think is pretty, let's say, easier to understand than other approaches out there for semi-definite programming. And what we get is both classical and quantum algorithms. The classical algorithms we've learned recently have roots in prior work of a famous person in optimization named Nesterov, and I'll comment on that as we go along. So connecting to this initial comment, why are they intertwined? Well, the fundamental constituents of quantum theory, as we learn them in quantum information, quantum states, measurements, and channels are all described by positive semi-definite operators that have constraints on them, right? A quantum state is a positive semi-definite matrix with a trace 1 constraint. A measurement is a collection of positive semi-definite operators with a constraint on their sum, that the sum should be the identity. And channels are in one-to-one correspondence with what's called Choi operator, and that itself is a positive semi-definite matrix with a partial trace constraint. So what happens is that when you want to optimize if you want to do an energy minimization, then you're minimizing the energy of a Hamiltonian with respect to quantum states. That's a semi-definite program, right? If you want to look at the error probability when you're using a set of states for communication, you're minimizing the error probability over all possible measurements. That is also a semi-definite program. And so when you encounter these problems of fundamental interest, you're inevitably faced with semi-definite programs. And so what's happened is that this theory of semi-definite optimization that was developed as an offshoot of linear programming, linear optimization in the 60s and 70s, mostly by people working in optimization and not intersecting with quantum physics. What has happened is that the findings of those communities have greatly contributed to quantum physics, to the physics community. And so the question that we pose is like, what can quantum physics lend to understanding semi-definite optimization, given this intricate link? And can these insights from quantum physics, in particular quantum thermodynamics, contribute to our understanding of semi-definite optimization? And that's our sort of motivation for this work. And we've addressed this in a way that you'll see in the forthcoming slides. So what we do in this work is we show how physical intuition coming from quantum thermodynamics can be used for understanding SDPs and for developing classical and hybrid quantum classical / variational algorithms for solving SDPs. Remarkably, many of the ideas that I'll present for the classical part go back to a single page of a 1962 paper by a famous physicist named Jaynes. A lot of people know his name from the Jaynes-Cummings model that appears in atomic and optical physics. He's also very well known for writing a series of papers that link information theory and statistical mechanics, that link what were prior to his papers somehow disparate fields. And in particular, he advocated for what's now somehow like common knowledge, the maximum entropy principle. And that can be succinctly summarized as saying, if you don't know anything about a given probability distribution, other than it should satisfy certain constraints, then the natural distribution to use is the one that maximizes the entropy subject to those constraints. So he talked about that in the classical context and in the quantum context. So he said, given if you're trying to determine a density operator that describes the state of the physical system, without any other knowledge than certain constraints that semi-definite quantum state should satisfy, you should pick it to be the one that maximizes the entropy subject to those constraints. So that's called maximum entropy principle. And mathematically, that's equivalent to free energy minimization, which is something that will come up later in the talk as a guiding principle for linking quantum thermodynamics and semi-definite programs.
Mark, is it okay to interrupt for questions? I actually don't know what
Please.
You prefer.
It's fine.
Okay.
Yeah.
Okay, so a very dumb and quick question. Is it the case that if you're maximizing entropy, the resulting distribution would be unique? Or is that a concern? Does it matter?
It is, yeah, it is. It'll be a thermal distribution with certain chemical potentials. So that will come up later. We'll see that in a direct way later on in the talk. We're going to be talking about free energy minimization, which, as we said, is mathematically identical to maximizing entropy. Okay, when I was so I gave this talk last week in Cambridge, and Hamza Fawzi is an expert in optimization theory, and he pointed me to work of a famous optimization person named Nesterov. And so I should really update this slide to also show Nesterov's picture, because the classical part of the algorithm we've learned after posting is essentially plainly there in a 2005 paper of his. So we're planning to update our paper to reflect that. Okay, but it doesn't appear that Jaynes or Nesterov were aware of each other at any point, even though they're kind of doing the same thing, actually. So that's very interesting. But again, Jaynes was a physicist, and Nesterov is an optimization person. Okay, so what is a semi-definite program? The input to the problem is a list of D by D Hermitian matrices that I'm calling big C and A1 through A little c, and these real numbers. And so an SDP in standard form, there are different versions of what is standard form, but most textbooks and literature that you consult agree that this is the standard form of an SDP. And it's described as minimizing a linear objective function subject to affine constraints. And so this objective function is linear in X. X is constrained to be positive semi-definite operator, so its eigenvalues should be non-negative. C, as we said, is some arbitrary Hermitian matrix, and A1 through AC are Hermitian matrices. And X, the minimizing X should satisfy this list of constraints. Okay, so, and the goal is to compute this optimal value. And so this is how it is presented in most optimization works. And what's missing in these works is some kind of connection to physics. And so that's what we're going to be talking about. Semi-definite programs have applications across the board. We mentioned their connection to quantum mechanics due to the link of the postulates and optimization tests, but they also appear in many different fields, some of which I've listed here. And in computer science, they play a big role in relaxing certain computationally difficult problems to get bounds on optimal solutions. So they're somehow very important in theoretical computer science. Okay. And of course, they've appeared in quantum information in many different contexts, in communication, in computation, in complexity theory, etc. Okay. Now let's talk about a quantum thermodynamic system. So a general quantum thermodynamic system is described by a Hamiltonian that we'll call H, and a tuple of what we'll call non-commuting charges that are conserved and have expected values. Okay, and this term conserved means that the state of the thermodynamic system, the expected value of like the ith charge should be equal to some fixed number, and that represents some kind of conservation law for the thermodynamic system. Mathematically, these matrices are also D by D Hermitian matrices. The kind of thing we'll be thinking about when we talk about quantum algorithm is D is 2 to the little n, where n is the number of qubits. Okay, in physics, the Hamiltonian describes the energy of the system, and the charges correspond to quantities that are conserved while the system is interacting with an inaccessible environment or reservoir. Examples of charges. So if you've taken a course in statistical mechanics, you learned about like grand canonical ensembles and chemical potentials. And examples of these charges will be particle number. Maybe the total number of particles in the system is conserved to be some fixed number, even though the system and environment could be exchanging particles. So that would be a constraint. Another kind of constraint is electric charge. What you learn about in a statistical mechanics course, at least what I read in the papers of Nicole Younger-Halpern, who's thought about a lot of these non-commuting issues with quantum, is that in a standard course, you just assume that these matrices are all commuting. And so the theory simplifies a lot. Whereas in a quantum thermodynamic system, they need not commute. Okay. So in quantum thermodynamics, a problem of interest is the energy minimization problem. So to minimize the energy, that's the expected value of the Hamiltonian with respect to some state, subject to these constraints on the charges, right? And here I'm using notation common in physics. Curly D is the set of D by D density matrices, so D-dimensional quantum states. And this notation is common in physics. It means it corresponds mathematically to this trace. And this is interpreted as the expected value of the Hamiltonian when the state is rho, and similar notation for here. And this captures the conservation of the ith charge. So if you're comparing what we talked about with a general SDP to this problem of interest in quantum thermodynamics, you'll notice that they are identical mathematically. There's no difference between them other than the operator we're optimizing over has a trace one constraint, okay? So they're very, very similar. And so that kind of tells us that, you know, SDPs can be used for understanding quantum thermodynamics, and quantum thermodynamics should be useful in understanding SDPs. And that's the direction we're going in. Okay.
One quick question.
Yeah.
So generally the SDPs can also have inequalities as constraints. Right?
Yeah.
Like, here are we only dealing with equality? Like, does it change anything for us? Like, does
That's
it make
right.
the problem easier?
So there's ways to map equality constraints and inequality constraints to each other. If there's an inequality constraint, you can add what's called a slack variable to, it's like you're increasing the dimension of the system such that all the inequalities will become equalities. So there's simple mappings between them. And that's why, you know, somehow with equality constraints, people focus on this as a standard form. But it's a good question. There's ways to map between them. You know, an equality constraint is equivalent to two inequalities, right? And then, as we said, an inequality constraint can be converted to an equality constraint via what's called slack variable. And there's ways to account for that in the algorithms that come later. So we can talk about that later as well.
Okay, thank you.
Okay, good. All right, so these problems are essentially identical mathematically. As we said, the only difference is that energy minimization is performed over quantum states. And then now we return to this question, can we use physical intuition for understanding SDPs? Okay, so what we're interested in quantum thermodynamics is energy minimization. An intuition that we can use from physics is that real physical systems, they don't operate at zero temperature, but they operate at a strictly positive temperature. And so the intuition is that rather than focus on this energy minimization problem, we can focus on minimizing the free energy. This H minus TS is a famous formula in physics for free energy. And H is the energy term that we had before, and minus TS is this temperature scaled entropy. And here we're going to use von Neumann entropy because we're in quantum mechanics. And when you subtract off the temperature scaled entropy, that's like the energy that you cannot make use of, that's somehow just like lost. But if the temperature is low, then the free energy is a very good approximation for the entropy, for the energy, and we can quantify that precisely, and we'll do that on the next slide. Okay, so von Neumann comes up once here, and then he's done so many things that his name will also come up later in the talk in the context of minimax theorem. Okay, so why is it useful to think about free energy rather than energy? Well, entropy has these fundamental bounds, right? It's non-negative and it's less than log D. This log D is the famous formula that appears on Boltzmann's tombstone. So these bounds can be used to derive this bound, that the free energy at temperature T is bounded from above and below by the energy, which is what we were interested in, minus this correction term. So what these inequalities indeed tell us that as temperature goes to zero, free energy goes to energy. That's intuitive. And it also tells us that we can approximate the energy by the free energy at low temperature T. So if we want to have error epsilon in this approximation, we would set this number here to epsilon. And if we solve for t, it tells us we would need the temperature of the thermodynamic system to be this small to get a good approximation. And in particular, what you see is the desired error, which we think of as a constant, divided by log of the dimension, which is number of qubits. So the temperature should be inversely proportional to the number of qubits. That places a demand on quantum algorithms that will come later that make use of low temperature thermal states to do this optimization. Okay, so given this approximation, we can shift our goal from the original goal of energy minimization to a free energy minimization problem at low temperature. Okay, so now we're going to do another step. We're going to use a concept called Lagrange duality, which has its roots in the basic idea of Lagrange multipliers from calculus. And we'll also use properties of a famous function, possibly the most important function in quantum information theory, called quantum relative entropy. And we can use these two concepts to rewrite the free energy minimization problem in a dual form, which is called a chemical potential maximization problem. So this mu is a chemical potential vector. Mathematically, they're going to play the role of Lagrange multipliers. Okay, and so to calculate the free energy at temperature T, what this formula is telling us is that we can instead try to solve the dual problem of maximizing this objective function over the set of all chemical potential vectors. This Z is the partition function for the system. Okay. And so that has this form. It involves big H, which was the Hamiltonian. I'm now using a shorthand. Big Q is a vector consisting of all the QIs. And this mu dot Q is a dot product. So for every constraint, there's going to be, for the ith constraint, there'll be a mu I. And so mu is a vector with elements going from mu1 to mu c. And this is just the sum over I of mu I qi, so it's a shorthand. And again, you see the temperature T appear in this partition function. Okay, so there was a question earlier, is the thermal state unique or something like that? Is the free energy, is the maximum entropy state unique? That's identical to the minimum free energy state being unique, and that is true. And it will have a form that we'll talk about on a slide coming up. And there is an optimal choice of the mu parameter vector here, and we'll address that later as well. Okay.
Mark, before we go on, a very quick question. So you seem to be implicitly assuming strong duality. Is that an assumption, or is that always true? Or
we're going to prove it.
So it holds. Okay.
Yes.
But I thought that everything was fully general in what you're describing so far. So I'm a bit curious how.
Okay, so that's a subtle question. Let me address it in this way.
I mean, the maximally mixed state is in the G-well set, right? So that already implies that you will have a strong duality.
Let me answer the question. This optimization problem might not have a solution. For example, if we set, so here we're optimizing over the set of density operators. And if we were to also set Qi to be the identity operator and little qi to be 2, then it would not be possible to solve. There's no density operator that has trace 1 and trace 2.
Right, sure.
So this would not be solvable. And the optimal value of this would be plus infinity. Okay. in the case that there exists a state such that all these constraints are satisfied, then it is solvable and strong duality will hold. And that kind of thing will come up as well. So like in the dual problem of the chemical potential maximization, I think when we do that, it's a little bit more subtle. The constraints are somehow approximately satisfied. And but my intuition there is that if these constraints are not satisfiable, then those mu i's will simply be infinity, And so it's kind of a case that's not of interest when these constraints are not satisfiable, right? It's like outside the interest. Okay.
Thank you.
Yes. Okay. Good. So we're going to talk about the duality proof, and somehow the question came at just the right time. So you might look at this and wonder, this equality between free energy minimization and chemical potential maximization has been asserted. What happened? Why is that true? I said Lagrange duality, blah, 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 properties of quantum relative entropy, blah, blah, blah. But let's go into some details of why that's true. So I'm going to show a proof, and there are different philosophies on whether one should show a proof in a presentation, but somehow this is so important that I think it's useful to go through it. So we'll try to go through it quickly. This was the original problem, free energy minimization. So what do? As our first step, we convert the constraints. We use Lagrange multipliers, which are these mu i's for each constraint, and we put those constraints in the objective function. So we convert a constrained optimization problem to an unconstrained one. What is the intuition here? We want to minimize over states for which these constraints are exactly satisfied. And you can think of what's going on here with the Lagrange multipliers is that if the constraint's satisfied for the state rho, then this term here is equal to 0, and the Lagrange multiplier will play no role. However, if it's non-zero, then a choice of mu can be made to make this term blow up to infinity, right? And so, with these optimization problems, you can think of this as like a two-player game where a first player gets to play a state, and then this supremum corresponds to a second player who's like checking whether the state that's played by the first player satisfies the constraint. If the state rho does not satisfy this constraint, then this second player can say, well, you didn't satisfy the constraint, so boom, you get an infinite penalty, and you lose in your goal of minimizing this objective function. So that's how you can think about this first step.
Mark, another dumb question. So why don't we use max instead of sup? Is there like some obvious answer?
I think it would be fine to use max. Well, no, sup, I think we do need sup here because in case the constraint's not satisfied, then we want this to blow up to infinity. And so we have to go outside the real numbers and we have to take a supremum.
And why do we want it to blow up to infinity? What if it's just something large?
So what I was saying earlier is that we want this constraint to be exactly satisfied. And so if this player does not play a state that satisfies the constraint, they get an infinite penalty. Yeah. Okay. And so that's the only reason we can assert equality between these two. If you want the constraint to be approximately satisfied, then you could have like an upper bound on this mu.
Got it. Thank you.
Have a max instead. Okay, so the next step is somehow trivial. This term here in the objective function does not depend on mu, so the supremum can go to the outside. Okay, so we bring it to the outside, and then we notice that this term here is mu.q. We can put it over here. We can scoot this here, scoot this here. And then I'm putting minus, this term I'm rewriting here. So it's just algebra also. Okay, with a little more algebra, really basic, I'm just abbreviating this sum ui qi as mu dot q, as I mentioned before. And then we're bringing trace h rho here, bringing these together, bringing the entropy term here. Okay. Next step, highly non-trivial, fundamental. This is where von Neumann's name comes up again in the context of a minimax theorem. So the only change from the second to last line to the last line is we're flipping the order of optimization. So that's non-trivial. You can't always do that. You have to check whether certain conditions hold. In this case, the set of density operators is a convex set and it's compact. The set of reals is convex. So those are two conditions for the minimax theorem to be applied. The objective function is linear in mu, so therefore it's concave in mu. This term is linear in rho, so therefore this term is convex in rho. Entropy is well known to be concave, so that means negative entropy is convex. So that means this objective function is convex in rho. So all the conditions of the minimax theorem apply, and therefore we can swap. So the famous quote that's attributed to von Neumann, there are multiple quotes attributed to von Neumann. We don't know whether they're true, but we always retell them anyway. So the quote for minimax theorem is that he said, "I thought all of game theory was completely uninteresting until I proved the minimax theorem." So gives you a sense of its importance. It also tells you, we're talking about this order of optimization is like a two-player game. This order corresponds to a first player playing rho and a second player getting to react to that choice of rho with a choice of mu. And in a typical game, if you get to go second, you have an advantage because you can react to whatever the first player did. What the minimax theorem says is that the order of play doesn't matter. So they can instead play in the opposite order, and they'll still reach the same optimal value of the objective function. And so the optimal value, if you want to visualize in 3 dimensions, will be a saddle point of the landscape. Okay, or also like an equilibrium point. Okay, let's continue with the proof. I want to, so we apply the minimax theorem. I want to focus on the min expression and not worry about the supremum for now. So we're going to think about the min expression with a fixed mu in there. Okay, we're going to introduce this notation for parameterized thermal states. I'd already talked about this a little bit previously when we saw the partition function. So a parameterized thermal state has this form that involves the operator, the Hamiltonian and the charges from the thermodynamics problem. And this mu is like a parameter that can be tuned, and that will play a role in algorithms that we use for semi-definite optimization that come up later. These states are also called in the literature non-abelian thermal states. I think I've even seen the term generalized Gibbs ensemble or grand canonical ensemble. In quantum machine learning literature, these are called the quantum Boltzmann machines. And we've been writing a sequence of papers recently on quantum Boltzmann machines where they come up. So this will come up on the remainder of the proof. And as we said, we're also going to use quantum relative entropy. We've already applied the Lagrange duality because we use Lagrange multipliers. And now we're going to apply the other tool I mentioned, which is quantum relative entropy. So this is a famous function in quantum information. And as I said, possibly the most important one. It was proposed by Umegaki in 1962. If you remember that year, 1962, I mentioned that was Jaynes's paper, was also 1962. As far as I can tell, Jaynes and Umegaki were not aware of each other, even though Jaynes was using quantum relative entropy on his one-page proof of, or one page of his paper where he stated many things about maximizing entropy in the presence of non-commuting charges. Okay, so relative entropy of states has this form. If you remember the formula for the von Neumann entropy, you can recognize the first part as negative of von Neumann entropy. And the second part is this term here. I think it's often called cross entropy. Key property of quantum relative entropy is that it's non-negative for states, and it has this faithfulness property. It's equal to 0 if and only if the states are the same. So we can continue with that last line that I mentioned on the previous slide. And it's just a few more steps of algebra to see what's going on. So mu dot q does not depend on rho. We can bring the min over rho inside. Nice. We can factor out the temperature T so that there's no T here, and we have divide by T here, so that's simple. The next line is some algebra. I want to get this in the form of a quantum relative entropy, like we had on the previous slide. So we can introduce a minus sign and another minus sign. That's this and this. And then we can take the logarithm of the exponential. Those are inverse functions, so they cancel their action. And we get this expression. Then this is starting to look very close to what we had in the previous slide for quantum relative entropy, right? Negative entropy minus this cross entropy. So this is now like negative entropy and almost like a cross entropy of rho and this operator. So if I take this operator and normalize it by its trace, which is the partition function. So if I divide by zt and multiply by zt and do a little bit of math, we can recognize this line as quantum relative entropy minus the log partition function. Okay, so we're recognizing relative entropy in this expression. Now you see this term here has no dependence on rho. It just depends on mu and h and q and t. Okay, and this is the only term left that depends on rho. But quantum relative entropy, as we said, has these properties of non-negativity for all states, and it's equal to 0 if and only if the states are the same. So that tells you to minimize this expression now, simply pick rho to be a parameterized thermal state. And then this will be equal to its minimum value of 0. And that's how we get this expression that appeared on the previous slide with chemical potential maximization. This step right here of minimization is quite important for interpreting what's going on with free energy minimization. Originally, we thought we'd have to minimize this expression over all possible states, but this is telling us that it suffices to restrict the optimization to these parameterized thermal states. So there's nothing else to consider in the optimization problem. That's really nice because it simplifies the search immensely. Rather than having to optimize over all states, we simply need to focus on these parameterized thermal states. Okay, so that's a key insight. And it tells us that if we want to do free energy minimization, we can switch our goal to this chemical potential maximization problem. I've occupied 40 minutes. Do I have an hour?
We have an hour and a half actually, including
Yes,
questions.
yeah.
So
Okay.
you
Right,
can
so
take
we
as
can
much
go-
time as you want.
We can go as a reasonable pace. Okay. So our goal
One
now
question.
is to switch to this optimization problem. There's a question?
Yeah. So why do we switch from minimizing the energy to minimizing the gift state? Like chemical. Sorry, the thermal. The free energy. Like, is
Okay.
it cause like creating gift state easier than creating ground state, or like can we have the same problem but like keeping the like energy minimization there?
Okay. So our original goal was energy minimization, right? And we said, let's instead do free energy minimization. And when we do so, we can approximately minimize energy subject to a little bit of error, right? So then we said, that's fine. We'll tolerate a little bit of error. Anyway, when we do these optimization algorithms, there's always some error, and the complexity of the algorithm always depends on the error. So that was our first step. And then the second step is to use this duality to say that this minimization problem is identical. This is an equality. So this was the original free energy minimization problem. And what we now proved is that free energy minimization is equal to chemical potential maximization. And so due to this equality holding, we are switching our goal to instead maximize the chemical potentials. And then in that proof we saw that in doing this minimization, it suffices to focus on parameterized thermal states.
So finding thermal state is like a special, like finding the ground state is like a special case of finding the thermal states. Like, can we have a similar dual problem, like keeping the energy minimization?
Yes, you'll have a dual problem, but the issue with it is it won't be somehow smooth. And so when you want to use an algorithm, so our next goal will be to use a standard gradient-ascent algorithm to find these mu's. So we'll actually argue that this is a concave optimization problem, and this objective function is smooth, and so we can give nice guarantees on the runtime of the algorithm by essentially like smoothing the objective function to incorporate entropy. And Nesterov, the optimization person, everything I'm describing, he simply called it smoothing technique, but there wasn't any physics interpretation. So that's the idea. By having a little bit of strictly positive temperature, it somehow smooths the optimization problem. And then as we saw, like the optimal states will be these parameterized thermal states. You can think that for 0 temperature, that is literally like in this expression, you take the temperature to 0 and it converges to something, right? And you could focus on that, but somehow it's nicer to have this non-zero temperature. And anyway, as we said, that's what will happen in a physical system. So when we go to designing quantum algorithms, it's useful to be able to have this freedom in working with thermal states rather than like directly with the ground states. Okay.
Yeah, I see. Thank you.
Sure. Okay. So we're now switching our goal to this chemical potential maximization. If you do some further calculations that I'll skip, you can show the partial derivatives of the objective function, which you collect together the vector of these partial derivatives, that's the gradient. It has this nice and simple form. So, and then this form will have a thermodynamic interpretation when we talk about a gradient-ascent algorithm, how you can think of like the system trying to balance things out such that the conservation laws are obeyed, okay? So that's the gradient. Also, if you compute the Hessian of this objective function, which is needed to understand the curvature of this objective function, if you compute it, you find that it's equal to the negative of something called Kubo-Mori information matrix that has this form. Remarkably, this also appeared in Jaynes's paper in 1962, but it doesn't show any proofs. And this concept of Kubo-Mori information matrix, it's a certain kind of quantum Fisher information matrix that has appeared in the context of metrology and more abstractly, this field called quantum information geometry. Okay, so the Hessian, so as we said, the Hessian of the objective function for chemical potential maximization is equal to the negative of the Kubo-Mori information matrix. The Kubo-Mori is actually positive semi-definite, okay? That can be seen, and this is certainly not obvious. If you plug into quantum relative entropy a given thermal state and one that's nearby this one, and you do a Taylor expansion in terms of this epsilon, this vector, which is telling you like how near you are to the original state. If you do a Taylor expansion, there's going to be a 0th order term, a 1st order term, and a 2nd order term. The 0th order term will be when epsilon 0. As we said with relative entropy, if the arguments are the same, then it's 0. So actually the 0th order term in the Taylor expansion is 0. 2nd order term involves the gradient. But as we said, the quantum relative entropy is non-negative for states, and it's equal to 0 if and only if the states are the same. So that means we're actually doing this Taylor expansion about a minimum of the relative entropy function. And as we know from calculus, when we the derivative around a minimum is 0. So that means the 1st order term involving the gradient will also be 0. That leaves you with the 2nd order term, which when you do some lengthy calculations, you see is this Kubo-Mori information matrix. So relative entropy is non-negative. This epsilon is some parameter we can tune. And because this is non-negative, that implies that this expression will be non-negative. And it holds for all small epsilon vectors that you can tune. That implies this matrix is positive semi-definite. So that tells us that the Hessian of the objective function of interest is negative semi-definite, and therefore this function is concave in mu. And so that's very nice for optimization. We want to do this maximization. And if the objective function is concave and what we want to optimize, then we have a convergence guarantee that it can be solved by gradient ascent. And we can, if we have a bound of the largest singular value of the Hessian, that will also tell us like something about the curvature of the surface we're trying to optimize and how long it will take for gradient ascent to converge. Okay, so a summary of the approach we developed is this. We originally were interested in energy minimization. We said, let's instead study free energy minimization as an approximation of the original task. Let's use Lagrange duality to rewrite the free energy minimization as a chemical potential maximization. And then as we've argued now, this can be solved by gradient ascent. And we can get a solution to this problem if we set the temperature to be low, and in particular this low. Okay, so a classical algorithm for this problem looks like this, and this is all you need to specify the algorithm. So it's very simple. As we said, this will solve energy minimization, and it will also, in turn, there's a way to modify it to solve general SDPs. So the algorithm, basically what the algorithm is trying to do is search for the optimal mu, right? Which we know is unique because this objective function is concave. Actually, it's strictly concave. So that was a question from earlier. Is the optimal state unique? The answer is yes. And now we're trying to find that state approximately via gradient ascent. So the idea is to initialize the chemical potential vector to the all zeros value. And if we're doing that, remember those thermal states had H minus mu dot Q. So if mu is 0, that mu dot Q term will not be there. So that means for this algorithm to work, we need to be able to initialize it to a low temperature thermal state of the Hamiltonian H. So, that's a demand for a classical algorithm, and later it will see that it's a demand for a quantum algorithm. Okay. We then set the learning rate of the gradient ascent algorithm to be some number in this range, where this L is a smoothness parameter that we'll identify later. That's, as we talked about, related to the curvature of the landscape, which can be determined from the Hessian. This radius is like the size of the search space we're going to look over. So we're trying to look, mu, the parameter, the chemical potential vector, is a c-dimensional real vector. And so we have to look in that space to try to find mu star, which is the optimal value of mu. So radius is just like we have some guess on a Euclidean ball that contains the optimal value. And this R is the radius of that Euclidean ball. So we have to have some sense of where the optimal solution lies. But we can, have a large ball that contains it. Okay, so you need that kind of guess for this to work. And that's common to all gradient ascent and descent algorithms. The number of iterations we set to be this. So as we're proceeding, we're modifying the chemical potential vector, right, to either increase it or decrease it. And the interpretation here is that if the expected value, so this is a shorthand actually for a vector consisting of the QI charges, and this is also like a shorthand as well, big QI. The interpretation here of what's happening with the algorithm is that suppose that the ith constraint for the ith charge is larger than the expected value, then what this is telling you is you need to add charges to the system. And you can do that by increasing the ith chemical potential. Whereas if this number is negative, that means you need to remove those charges from the system. And so that's what this gradient ascent algorithm is doing, to try to find the optimal mu, such that the constraints will be satisfied. Okay. At the end, the algorithm, after this number of iterations, it outputs a chemical potential vector. If you run it this number of times, then from very well-known results on convergence of gradient ascent, we know that this value will be like epsilon close to this value, the optimal value of the objective. Okay. And if you plug into the math that we did on previous slides, this objective function will evaluate to this expression here. And so in the algorithm, we could output this expression that would involve the temperature scaled entropy also. But we're choosing not to do that because it's simpler to evaluate this rather than to evaluate entropy. It's not a big deal classically, but when it comes to a quantum algorithm, it'll be much easier to estimate these expectations of these observables rather than have to estimate entropy as well. Okay. And when we do this, as we said, entropy is less than log d. And so the error we incur when doing this approximation will be less than t log d, which we set to be epsilon anyway. So that's the classical algorithm. And if you run this for this number of steps, you're guaranteed to be within the desired accuracy. So gradient ascent is guaranteed to converge. I learned recently about some other major contribution of Nesterov is that there's a slightly different way to do gradient ascent where the number of iterations will be the square root of this number. And that method is called Nesterov accelerated gradient. And to do it, the amount of computation you incur is basically negligible, compared to this. But this algorithm is easier to understand than the Nesterov accelerated gradient. Okay, to figure out the number of steps we need to identify the smoothest parameter. So the next slide will be about that. If we set the smoothness parameter, so the smoothest parameter has to be larger than the largest singular value of the Hessian. Okay, in order for this to work. As we said, the Hessian indicates how curved the landscape is. And if the landscape is very curved, then that's telling you should take smaller steps at each step of the algorithm. Is where if it's very flat, then it tells you you can take larger steps. So the smoothness parameter is related to that. The Hessian, as we said, is this negative Kubo-Mori information matrix. We can bound the absolute value of the matrix elements of the Hessian. And when you do so, you get this. That you can see as arising. There's a 1 over t. That's where this 1 over t is coming from. There's this term involving qi and qj. There's a second term involving qi and qj. So because there's 2 of them, you get this factor of 2. If you want to bound this absolute value, you would use like triangle inequality. And when you do so, you'll get that this term here is less than the infinity norm because it's these observables evaluated on states. And then if you use Holder's inequality, you'll get that this term is also less than the product of the spectral norms of qi and qj. Okay. If you sum the diagonal terms of this upper bound, because the Hessian is positive semi-definite, that implies an upper bound on the Hessian's trace norm given by this. So the way you think about this is we're just setting I equal to j and summing over all the diagonal elements. And there's c of them, so you get this sum, I going from 1 to c, and this factor of 2 over t. So that gives an upper bound on the trace norm, and the trace norm is an upper bound on the spectral norm of the Hessian, which is equal to the largest singular value. So then we can take L to be this, and the algorithm will be guaranteed to work if we make that choice of smoothness parameter. Okay, so we said the temperature T has to be roughly epsilon over log D. Plug that in, and you get this expression for the smoothness parameter. Okay, so if we plug back into the requirements for gradient ascent, previously, we said it's well known in gradient ascent literature that if you have this number of iterations, it's guaranteed to converge. So if we plug in this choice of the smoothness parameter that we identified in the previous slide, we get that the number of iterations of the algorithm is given by this number. So you have radius over epsilon squared log d, and then this sum here. Critical thing is log d. So the number of steps is logarithmic in dimension proportional to the number of qubits. So that's very nice, not only for the classical algorithm, but also for the quantum algorithm that's coming. Okay, so that's the number of iterations, and it gives you a sense of this Jaynes-inspired algorithm for energy minimization. This is telling us number of iterations, but we should also look at what's involved in each iteration. You have to compute this expected value and this expected value. So if the matrices are very large, that might be hard to do on a classical computer, right? Maybe you could do something very clever with matrix product thermal states that would work for some systems. But I think as you get to lower temperature, that's going to get harder and harder. And so then that's where it suggests we need a quantum computer to evaluate these expressions. Okay.
There
That's
may
the
be a
summary of the
question.
classical algorithm. Yes.
Kishore, do you want to ask your question? I see you have the hand raised.
Yeah. So, Mark. So basically, I was thinking that let's say like you give a, like upper bound on the singular values of, like of the Hessian matrix. Like, do you have some kind of a lower bound also? Because then that will imply strong convexity, and then your convergence can be faster.
That's a great question. That's a very good question. So in our paper, we don't address that, but there is a paper, I think it was on the archive in 2020 by Anurag Anshu and others. It got published in Nature Physics. And I think it's called
Hamiltonian learning paper, like
sample efficient learning of many body Hamiltonians. So one of the major contributions in that paper, they were considering a very similar objective function to what appears. Actually, their objective function was essentially this without mu dot q, and they didn't have the minus sign. So they proved in their paper that if the Hamiltonian matrices are quasi-local, and they have a certain definition of that, then they get a lower bound on the Hessian, on the minimum singular value of the Hessian, and they get strong convexity. And so that was one of the major claims of that work. And so, for whatever Hamiltonians they have that are quasi-local, that also applies here, and this can be improved to have strongly concave objective function and much faster convergence of gradient ascent. We comment on that at the end of our paper. That's a very good observation and question. It would be great to study that further and possibly expand the scope of Hamiltonians for which this could be shown to be strongly concave. Okay.
And sorry, dumb follow-up question. So
Sure.
What is the definition of strong convexity? I mean, I could look it up, but maybe
so I think it's that somehow it looks quadratic. That's a rough way to describe it.
Like you can say Hessian is basically greater than equal to some constant times identity matrix. So the lowest eigenvalue, like singular value, is upper bounded by. So normally it's like greater than equal to 0. But let's say if you say some constant times identity, then basically you are saying that every singular value is greater than some smallest value. So yeah, like I mean, it's in that sense it's strongly convex. Like it's very sharply, like I mean, like you can reach there faster. Like if you visualize, yeah, it looks quadratic.
Yeah, that's a good definition of. So if the lowest singular value, if all the singular values were greater than mu, or sorry, then like little m or something like that, it's said to be m strongly convex. And then this m would appear in convergence guarantees for gradient ascent, and it can go much faster.
Yes. Thank you.
Yeah, thanks for that comment and discussion.
I have another question.
Sure.
Can you go back to the slide where show the algorithm?
Yeah.
Yeah. So like, do we start with the thermal state? I mean, like, isn't it in and itself like a hard problem to solve? So
That's right.
it does the algorithm only work for like instances where the thermal state is known or easy to predict?
So right now we're presenting a classical algorithm, and if these matrices are small, then on a classical computer you can calculate these thermal states. But if the Hamiltonian corresponds to n qubits, then it's a non-trivial problem to be able to prepare these low temperature thermal states. If you look out on the archive, there's been tons of progress on quantum algorithms for thermal state preparation of particular physical systems. And there was even a tutorial at the recent QIP conference. I was not able to make it there. I've been looking at YouTube every once in a while to see if that lecture will appear. I still have not seen it online, but I'm waiting for that or some slides to appear. And presumably you get a nice summary of all the latest progress on algorithms for thermal state preparation. It's a very hot topic. Recently, I visited the company Quantinuum in London, and many people there are working on thermal state preparation. I think many people in various quantum computing companies have efforts focused on thermal state preparation due to their significance in optimization tasks and beyond. But you're right that in general, like for a general Hamiltonian, this is not an easy problem. And for very low temperature, it's essentially equivalent to being able to prepare the ground state, which is not an easy problem for a quantum computer. Okay. So given that, let's now talk about a quantum algorithm. It's now about 24 minutes remaining to the total time. So the question is, how do we quantize the classical algorithm? Quantize, I mean, as you probably know, turn it into a quantum algorithm. So let's inspect the classical algorithm. These parts can stay the same, essentially the same. We might have to do little modifications. This part we should do on a quantum computer, which is simply estimating the expectation of the observable of the ith charge on the thermal state at temperature T and with this chemical potential. And then similarly, we have to estimate this observable as well. Okay. And then if we do that, we have a quantum algorithm. And rather than doing deterministic gradient ascent, this algorithm will be doing stochastic gradient ascent, because this estimate will be a random variable that's meant to be an estimate of this deterministic value, and similarly here. Okay, so the algorithm remains essentially unchanged, but two lines become quantized. Okay, so let's talk about the quantum algorithm. Now we're thinking about these matrices are really 2n by 2n dimensional, and it's going to be too hard for the classical algorithm to estimate these observables. As we said, maybe you could do something very clever with matrix product thermal states, but like a naive method will take exponential time to calculate these quantities. Okay, so we're going to instead try this on a quantum computer. What are the requirements for the quantum algorithm? We have to be able to estimate this observable and this one. So to be able to do that efficiently, we need to be able to efficiently prepare thermal states at this temperature. As we discussed, that is by no means easy, and it's sort of the topic of cutting edge research in quantum algorithms. Okay. We also need to be able to efficiently measure these observables. That's not as hard because for Hamiltonians of physical interest, they're easy to measure. Okay, and we're going to focus on the sample complexity, which is the number of thermal states needed for the algorithm. Why is it useful to do that? Well, it's like every week there's new algorithms coming out on thermal state preparation. They're getting better and better. And so whatever algorithms come out, they can be plugged into this algorithm to get a sense of the overall complexity of our algorithm. Okay. And so this has the effect of separating out like a thermal state preparation subroutine. And as we said, there's been much progress on this topic. Okay, so we're now going to assume that these the Hamiltonian and the ith charge is a linear combination of Pauli strings of this form, because that corresponds to many physical models of interest, like Ising model, Heisenberg model, etc. These observables are efficiently measurable by a sampling approach if the one norm of these Pauli coefficient vectors are not too large, if they're polynomial in the number of qubits on which these Hamiltonians act. And A sampling approach to measuring these is essentially you take these coefficients, you normalize them by their one norm, and multiply by that also. When you do that normalization, they become a probability distribution. And then it's like you just pick a j at random, measure that one, and repeat this procedure and calculate a sample mean. And that will allow you to estimate these expectations. And the amount of time it'll take to estimate these observables is given by this and this. And you get this from standard Hoofding bounds, which tells you if you want accuracy epsilon, you'll need this number, 1 over epsilon squared repetitions. And if you want success probability, 1 minus delta. The dependence is much milder, log 1 over delta. Okay, so then the way we modify the classical algorithm is very straightforward, right? We just use the quantum computer to estimate this expectation. You get a value, plug that into gradient ascent like we had before. And then at the final step, you use the quantum computer to estimate this expectation and plug that into the final output. And so as we said, the algorithm is employing stochastic gradient ascent because this part's stochastic, this part's stochastic. You're using a quantum computer. And we get convergence guarantees for the algorithm, the number of iterations required, because as we said, the objective function is concave in mu. So then the number of iterations for this algorithm is essentially the same as what was required in gradient ascent, but the difference is the number of samples per iteration is this amount. So, and then that, as we said, comes from Hoofding bound. So then to get the overall number of samples of thermal states you need, you just multiply the number of iterations of the algorithm, which is this m, by the number of samples of thermal states you need per step of the algorithm. You multiply these two expressions and you get this. So you see here there was epsilon, 1 over epsilon squared, 1 over epsilon squared, it makes 1 over epsilon to the 4th power. The radius dependence is again square. And nicely, you know, the dependence on the algorithm is proportional to log d, which is number of qubits. Okay. And if each of these norms is, let's say, constant, then you see that the dependence on the number of constraints is c squared. Okay. So there are semi-definite programming algorithms that have a large number of constraints. And if the number of constraints is too large, then this algorithm is no good. This algorithm is good when, number of constraints is small, and when you can efficiently prepare low temperature thermal states. That's like the sweet spot we look for potential quantum advantage. If you have a situation where you have these Hamiltonians where the thermal states are efficiently preparable at low temperature, but then these expectations are difficult to estimate classically, that's the potential sweet spot where there could be a quantum advantage. Okay. Good. So that's actually the bulk of what I wanted to talk about. There are other things as well. Are there any, there have been lots of nice questions and discussions throughout. I guess I'll ask if there's any questions now, because it's a natural pausing point before there's basically 2 more things I want to do, which is talk about how do you do a general SDP and not just energy minimization, and then how do you incorporate second order information in gradient ascent, this is called Newton step, to have even possible faster convergence.
Can I ask a question?
Hi, Mark, one question.
Yes. Either order is fine.
Yeah. So let me ask. So if we look at the energy minimization problem, there is
Yeah.
rho, right, density matrix. So if we can replace it with positive semi-definite matrix and move the trace condition inside the brackets, it is just an HDP, right?
I don't know if I followed what you want to do. You're talking about this
So
problem?
yeah, so rho is a density matrix.
Rho density matrix, yes.
Yeah. So instead of that, I will just write it is a positive semi-definite matrix and trace row of it is 1. We can write it inside the brackets, right?
Yeah.
I mean trace of qy equal to q small qy, where that is 1. That is exactly HDP now.
That's an SDP. Yeah. So actually, maybe this next slide is going to address your question, how we're going to do a general SDP. So maybe I'll do the slide and then we can revisit if you still have a question.
Sure.
And then we can address the second question after that.
Sure. Thank you.
Okay. So a general SDP does not involve.
Can I ask a question? Sorry.
Oh,
Sorry.
can I just proceed as we said?
Sure.
Okay. So a general SDP, there's no trace x equals 1 constraint. So there's a question like, how can we use everything that we just talked about to solve general STPs? So a general SDP looks like this. What we can do, similar to how we made a guess on the search space for the dual chemical potential maximization problem, we can also make a guess on the search space of this problem. So that would be some radius big R that we're going to search within to find the optimal value, okay? And so it's like an extra constraint we impose. And the idea is that we have some guess on where the optimal solution is with respect to the trace norm. So if we do this, you can do a little bit of math to say that's essentially equivalent to like dividing the x by this radius r, and then you end up with an operator with trace less than 1. That's like essentially a density operator. And so when we divide by r, we multiply by r as well, and then we'll get the same value of the objective function. And so this reasoning allows us to reduce a general SDP to energy minimization, where this is an energy minimization problem. And what we do is we just multiply the optimal value by r at the end. So when we do that, it means that if we solve, in order to have an overall error of epsilon, it means we need to solve this energy minimization problem to error epsilon divided by r, okay? So then that will be reflected in the runtime of the algorithm. If we simply plug into the expressions from before, replace epsilon with epsilon over big R, we get this number of iterations needed for the classical algorithm, and this number, this sample complexity of the quantum algorithm. Okay, so that being said, let's return to the discussion regarding the first question.
Okay, yeah, thanks. So basically, it was nice to see, like 2 things there. Like one that yeah.
Sorry, Kishore, just to interrupt. I think yours was the second question.
Okay.
The first question was Gautam's. Is
the first question resolved?
Yeah, I think so. So if I understand correctly, we are saying more or less these 2 optimization problems are equivalent.
Yeah,
because we are moving from one to another in a way, it looks like.
Up to the scaling factor, yeah.
Sure. Yeah, thank you.
So I should say that if the scaling factor is very large, like let's say exponential in the number of qubits, then the algorithm's no good, right? So the scaling factor has to be only polynomial in the number of qubits for the algorithm still to be good.
I see.
So that's important. And then when you go and you actually look at problems like beyond energy minimization to things in, let's say, electrical networks and determining power flow, you encounter issues with this. Okay, let's talk about the second question.
Kishore, you can
Yeah,
ask.
so yeah. So basically it was nice to see that, like that thermal state there. And in that, like, I mean, I think back in 2017, 18, I don't know, at some point, Fernando Brandao, Amir Kalev, and other people had a paper on,
Yes.
I mean, that was like, like this fault tolerant, like quantum algorithm. So basically they look at the decision version and they
Yeah.
give an algorithm where, like, I think probably they were using multiplicative weight update, like if I yeah, and then like, they were working with this like, this thermal state, but yeah, I mean, I think like yours approach is different. Like, I mean, you like, I mean, so like, did you like, compare or anything, like, compared to,
Yeah.
like, like, does it give an improvement compared to that?
Well, this is a very good question, and I'm glad you're asking this because it's something I should have commented on earlier. Indeed, to recognize the existing literature on quantum algorithms for solving SDPs. The first insight was Brandao and Sforey in 2017, and they generalized this, as you said, matrix multiplicative weights algorithm to quantum. And they recognize that the operators involved in that algorithm are parameterized thermal states. And then later work built on that and had various improvements. So there are very strong connections between matrix multiplicative weights and what I'm talking about here, that you are updating parameters of thermal states in both algorithms. My take is that the way that we're presenting things here is somehow simpler because it's just a reduction to gradient ascent, and the algorithm is stated very simply. If you compare to their algorithms, there's a few more things involved in understanding what's going on. As far as our algorithm giving any improvement over the prior ones, we do have some discussion in our paper. I think I actually forget exactly what exactly the improvement is. I think it had to do with maybe the constraints, but I need to be careful there. So this kind of like big R over epsilon to the fourth power, and at least that's the same. This log D is the same. And then this little r, I think for ours is better. I think for theirs, we compared to the latest of Gilliam and Van Apeldoorn. I think in one of their expressions, they had little r to the fourth power, but I think they have better dependence on the constraints. Maybe they get like a quadratic improvement compared to us. So
also
yeah.
No, I mean, please continue. I mean, then I can now complete, like, say after you complete.
So what we view as sort of the major contribution of our work is recognizing this link between quantum thermodynamics and SDPs, and then being able to, once that link is established, being able to phrase things very simply in terms of gradient ascent. And so what this enables is there's so many different variants of gradient descent and ascent that are out there, that all of those, that arsenal can be used to attack this problem, And one of those is second order refinements that I'm going to talk about in a few minutes, if we have time. We have like 5 minutes. Okay. So is that good? We'll proceed to the last part.
One more question.
Kushagra, I mean,
Do we...
Okay.
Oh, I'm sorry.
Yeah, please.
No, you can go ahead. Go ahead.
Go ahead. Okay.
Oh, okay. Do we know anything about the regime where this algorithm can be useful? So basically, like, where preparing the initial state is easy and like finding the expectation values also quantum easily.
Yeah, so that's what I was saying. If we have Hamiltonians for which you can efficiently prepare these low temperature thermal states, then this is good. So the sweet spot is where it's quantumly easy to prepare low temperature thermal states, but classically hard to do so. And so that's not going to be all Hamiltonians, but we think that there should be some out there that will be, amenable to this, that can be used to have this kind of quantum advantage. At least we hope, So it definitely motivates more research in this direction beyond what's already going on. Okay, let me talk about the second order algorithm. This is the last remaining part. This is also, we consider one of our major contributions of the paper, like definitely going beyond the existing work. So the Hessian, as we said, has this form. It's the negative of the Kubo-Mori information matrix. I'm not going to show this proof. There's a fair amount of math involving, I guess we could summarize it as operator Fourier transform to rewrite this expression in this form. The problem with this expression right here is that it's not clear how you would use this to evaluate these matrix, to estimate these matrix elements on a quantum computer. Whereas when we write it in this way, identifying this phi mu as a quantum channel, then we can estimate these quantities on a quantum computer. So what is this phi mu? You pick a time randomly according to this probability density. If you plot it, it looks like, I didn't draw it on this slide, but I'm going to try to sketch it with my mouse. It looks like that. So we call it high peak tent probability density because it looks like a high peak tent. And the main thing about it is that when you pick a t at random, it's very likely to land around 0 because that's where the bulk of the probability mass is. So you pick a t at random, and then you do this Hamiltonian evolution according to these Hamiltonians in your SDP problem. And then that's this channel here. So with that, that tells us a quantum algorithm to estimate this quantity, and in turn gives us a quantum algorithm to estimate the Hessian. These ones are easy to estimate. It's again just expectations of observables for thermal states. Easy in principle if you have a good thermal state preparation algorithm. So then the quantum algorithm to estimate these terms looks like this. We're going to assume that each QI is a linear combination of Pauli's. So you'll sample T from the high peak tent, this random time. You'll sample for QI the coefficient for the Pauli string labeled by K. You'll sample L for the QJ1. And then you execute this circuit. This is a combination of Hadamard test and Hamiltonian simulation that combines two very basic primitives in quantum algorithms, one of which is Hadamard test, the other is Hamiltonian simulation. So you do this circuit, you prepare a thermal state, you sample this T, you sample this K, sample this L, and do this Hamiltonian simulation and these measurements. That's one trial. You keep repeating these trials, and what we prove is that that allows you to estimate this sort of cross-correlation term in the Kubo-Mori information matrix. So this we had discovered in earlier papers on, I have a paper with Dhrumil called Quantum Natural Gradient for Quantum Boltzmann machines. And so we developed that stuff there. But here we can use it for this Hessian estimation algorithm. So the algorithm, the quantum algorithm changes in just these two lines where you estimate the Hessian, which is the same as the Kubo-Mori. You then solve this system of equations, which tells you the gradient update. So if you've studied this Newton second order method before, this delta is essentially the gradient from before rescaled by the inverse of the Kubo-Mori. And then that can be used for possible faster convergence. So that's the modified algorithm. And for this, we didn't yet analyze the sample complexity. It's quite a bit more involved, but we've now found some papers on classical stochastic gradient ascent with second order that I think we can just plug into those and get statements about sample complexity for this quantum algorithm. So that we're leaving for future work that we're planning to do. Okay, that's summarized. That's the end of the talk. What did we do? We had this physical intuition from quantum thermodynamics that can be used for understanding SDPs. That was very pleasing from a physical perspective. The basic idea is summarized in this line. The original goal was energy minimization. We then approximate that by free energy minimization. We use duality theory to see that as equivalent to a chemical potential maximization, which we can solve by gradient ascent. So then this led to first and second order algorithms for energy minimization in SDPs. That's the summary. Future work, as I said, we want to do a rigorous analysis of the second order algorithms, sample complexity. We want to look at broader, there was the comments about the standard form maybe could be generalized. We talked about how to generalize it if those equality constraints or inequality constraints. There are broader classes of SDPs that appear, for example, if you study lecture notes of John Watrous. We want to generalize to that framework as well. We have a sense of how to do that now. And so we're planning things on that. One question that future direction I didn't have on the slide is, right now we're talking about a hybrid quantum classical algorithm. There's a question whether all steps in the algorithm can be quantized, right? So if you have a large gradient vector, can you represent that as a quantum state? And a lot of people have been writing papers about Stephen Jordan's gradient estimation algorithm. So that's a whole other direction that seems very interesting. And for the second order method, you would be solving a linear system of equations on a quantum computer, right? And so would that have benefits? That's a whole other direction, right? So we think that's very interesting. In the analysis, quantum relative entropy played a critical role. We've seen a lot of work on quantum Renyi relative entropies in quantum information. We wondered whether that could play a role. We had some thoughts there, but it wasn't quite clear to us at the moment what to do. And then, beyond finite dimensional systems, there's people trying to build continuous variable quantum computers, especially Xanadu, which is not so far from that's in Toronto, and it's not so far from Ithaca where we are here. So generalizing this whole framework to continuous variables in a sensible way seems interesting as well. And then, as we said, there's this lingering question of quantum advantage. There does seem to be a distinct possibility here. So one would hope for that. Thank you.
Thank you, Mark. And I think, your introduction was due. Sorry for that. There was power cut here, but anyway, you didn't require any introduction, and we all know you. But
Right.
Still, I would like to say, so it is pleasure to have you here, and you being my former PhD advisor. So Mark did his PhD in electrical engineering from University of Southern California. Right now, he's associate professor at Cornell University, and before he was in Louisiana State University. He is, pioneer in the field community and a lot of accolades, awards. I think list will go on. But mainly he has authored book which has shaped the research in quantum information theory, like you finding citations in many of that book, Quantum Information Theory, he has authored, and also co-authored book with Sumit Khatri, and I think Ludovico Lamy is also added now, perhaps.
Yeah.
At least it seems here. So Yeah, I mean, he has been doing pioneering work and now also in quantum computing. Yes. So, yeah, thank you.
Thanks a lot, Siddharth.
If there are any questions.
It's really a pleasure to be able to present to you and to others. And I hope we get, it's been a long time since we met up in person. I did go to India in August, but we'll have to try another time. So whenever you come to the US, maybe coming to the US right now is not so good idea. But
Yeah.
as soon as all this
Okay, so
stuff settles down, please, it'd be great.
yeah, sure. Yeah, any questions from the audience? I mean, it has been engaging discussion, so thanks for that. Like, this was nice and everything. Any questions?
Can you go to previous slide where you estimate the Hessian for the second order?
This one.
Yeah, like the next slide. So how do you deal with the integral over the time? Can you just explain it once more?
This is an average, right? So, we're not accounting for the discretization of this probability density. We're just kind of assuming that you can sufficiently fine grain this probability density such that you get a good sample. But the integral, this is an average, right? You can view this as an average of these channels. And so when you sample a t from from that density as well as these, and then you repeat this with a number of trials and calculating the sample mean, this is a common technique called Monte Carlo integration. Maybe you've heard of that before. It allows you to estimate quantities that are written in terms of integrals.
But the mean value of t could be is it necessarily 0, or can t be huge? So
the mean of t does not enter, the mean of this distribution does not enter the calculation. But if you're interested, the mean is anyway.
Is the time in the next step of the algorithm, like in the Hadamard test, what is the evolution time?
Oh, this probability density. I have another slide, maybe. Yeah, this is what it looks like. And so most of the probability mass is near 0. So if you pick a t from this density, you're highly, highly likely to get a small t. And so that tells us that the Hamiltonian simulation algorithm, the time is not large, and so that reduces the complexity immensely of that part of the algorithm.
I see.
Okay, I think in interest of time, yes, since many questions were already asked, and yeah, it was very clear talk. Also, if there are questions, I think we can reach out, people can reach out over email, right? Yeah, so thank you, Mark, once again. And yeah,
Yeah.
see you again sometime.
Thanks for having me.